All right, hey Calc students, today we're going to talk about 9-8 power series. I have some virtual notes for you, and this is the first one, so you'll have to bear with me as I navigate the system. I'm pretty excited to try this out with you, and so here we go. So 9-8 is about power series, and so by the end of the lesson today, you should be able to write a power series and use its radius of convergence. This is kind of the new piece for us. We've talked about power series a little bit before we left. We actually began the sort of big ideas of both 9-8 and 9-10 the last time we were together face to face. So these notes are actually meant to be an organized review of some concepts that really just solidifies and clarifies the big ideas of the power series and Taylor and Maclaurin series. So several, kind of talking about this power series idea, several important types of functions that were handed out earlier. If you remember, I kind of said these are the 4 big series and we passed those out. There's a couple more, but we'll review more of those in 9-10. But those power series are important types of functions that can be represented exactly by an infinite series, and that's called a power series. And so if x is a variable, then an infinite series of the form, all of this here, is called a power series. So you can see that using summation notation, it actually will equal that infinite series. And so more generally, an infinite series of this form is called a power series centered at C, where C is a constant. So you can see up here, it looks like we're centered at 0. And then back down here, we can actually be centered at any C. All right, so this big R is defined as the radius of convergence. So for part 1 of the theorem, and you'll kind of see on the next page, let's see if I can split screen this for us. Okay. So for part 1 of this theorem, and this theorem is for power series, right? The series converges only at C, or where we're centered, and that's it. For part 3 of the theorem, well, the radius is infinite, and that means that the series converges absolutely for all x's. But the set of R values then is called the interval of convergence, and in this case, we have just a set, this is kind of case number 2, where we just have one scenario in which we would converge. And so we call that interval of convergence, and one kind of important fact is that you need to check the endpoints of the interval to get a complete answer. So you'll kind of see what I'm talking about when we get to the next example, but we'll have a scenario where we can figure out where it's centered, and then from there, we can figure out, like sort of undoing this absolute value, we'll be able to get an interval. All right, so visually, if we have a series that only converges at where it's centered, right here, we'd get a single point. If the series converges over a specific interval, right, so this is sort of like plus or minus, then this is our interval of convergence. And you can see we have this interval or this radius here of convergence. And the series converges for all of x, well, that's the whole real number line. So you can see that we would always converge. All right, so the steps for doing this, let me go back to our single page, is we're actually going to use the ratio test. And the ratio test, that was a fun one. That was from 9-6 if you need a refresher. But we're going to use the ratio test for these to determine where the function converges. We're going to take the limit as n goes to infinity, and we can solve for x by setting the resulting expression less than 1. And that actually is because that's what the ratio test says, right? The ratio test says that a series will converge when the limit as n approaches of that, as it approaches infinity, would have to be less than 1. So we're going to set it, okay, well, let's assume that it is less than 1, and what would our x values be? And so this tells us the radius of the convergence. So then we're going to set up an interval by finding where the series is centered, and then we'll test the endpoints separately for convergence. And that's important because we need to know if we can include the endpoints in the interval or not. All right, so just a quick ratio test refresh. This is from 9-6 on page 627 for those of you who have your book. You can review that. If you don't have your book, well, here is a screenshot of that. And the part that we're focused on is this ratio test where it says the series converges absolutely when the limit as n approaches infinity. And this was our ratio that we were looking for, like the sort of the next term, right? The terminator for the next one. And then the one that we have, it has to be absolute value less than 1. So the limit of this ratio has to be less than 1 in order for it to converge. Okay, so we're going to use the ratio test to find convergence. Example 1 says, does the series converge or diverge? And then find the radius of convergence. So the first thing we're going to do is we're going to use the ratio test. And so we find this for the next term over. So we have x to the k plus 1 over x to the k. And that's going to equal the limit and as k approaches infinity. And we remembered our exponential or our exponent rules where we said x to the k or x to the k plus 1 is the same thing as x to the k times x to the first, right? Because we add exponents when we're multiplying the same bases. And that's all over this original x to the k. So you can see the x to the k divided by an x to the k will cancel, and we're left with the limit as k approaches infinity of the absolute value of x. Well, there's no more k, so the limit would just be the absolute value of x. So this would converge according to the ratio test when this limit, this absolute value of x, is less than 1. So far I'm thinking, okay, my interval of convergence, right, is going to be well between -1 and 1 because when we're thinking about the radius, right, if this is less than 1, the absolute value would tell us that if it was -1, right, or if I'd say -1/2, the absolute value of that would still be less than 1. So you can see here's where we've got our possible endpoints. So we have to test them out though. We have to check the endpoints and see if exactly at -1 and exactly at 1, would it still converge? And when we plug them into our original series, we see that it's going to diverge when we plug in -1. And if I plug in 1, well, that also is going to diverge. So since both of those diverge, neither endpoint can be included. And that's why we have the parenthesis, right, instead of that hard bracket. And so it's just between -1 and 1 and not including the endpoints. And so what is our radius? So what is the distance midpoint here? Well, the radius would be of 1. Okay. So example 2, it's going to ask us the same thing. Does it converge or diverge? Find the radius of convergence. So the first thing is we're going to use the ratio test. That's kind of like the thinking routine that I want you to have every time. And the limit as k approaches infinity of, and so I'm actually going to do the k plus 1 and the k plus 1 here. We're going to do that first. And if you remember the ratio test, it's actually this divided by x to the k over k factorial. But if we have a fraction over a fraction, that's our keep it, change it, flip it, or multiply by the reciprocal. So that's how we get x to the k plus 1 over k plus 1 factorial times k factorial over k to the x, or x to the k. So when we simplify this, right, I can kind of put my similar bases together. Oops. Okay, let's see. Okay, so now I have x to the k plus 1, which we know is going to be x to the k times x. And we can take care of our factorial as well here, right? Yep. So I have x to the k times x over x to the k times k factorial over k plus 1 times k factorial. We just practiced this right before we left. And you can see some of the things that will cancel out here. I'm going to move up here a little bit. All right, so then that is going to be the limit as k approaches infinity of the absolute value of x over k plus 1. And so what is this going to be? Well, when we think about k approaching infinity, we're going to get infinity on the bottom. So as we're bottom heavy here, we're going to get 0. So the limit is 0. So what's that mean? Well, the ratio test tells us that this, whatever the limit is, has to be less than 1 in order for it to converge. Well, since the limit was 0, that's always less than 1. And so we can say it converges, and it's going to always converge. So since it always is converging, we can see that it's going to converge from negative infinity to infinity, and the radius of convergence is infinity. Let's do another. So here we have, does the series converge or diverge, and find the radius of convergence. So again, we're going to use the ratio test. Okay, so let's try it. So the first thing we have to do is that ratio test. And so that means I'm going to do a k plus 1 and a k plus 1, right, everywhere we see. And this wasn't a fraction to begin with, so it is just k plus 1 factorial times x to the k plus 1 over our original terminator, right, that k factorial times x to the k. And remember the ratio test, we've always got this absolute value in it. So then in simplifying, we practice rewriting this, right? We can rewrite this as k plus 1 factorial is going to be the same thing as k plus 1 times k factorial. So the k factorials cancel. And x to the k times x to the 1. We can see that x to the k's will cancel, so we're just left with k plus 1 times x. Okay, so then we take a look and see, well, what's going on as k is going to infinity? Well, as k is going to infinity, we see, well, this is absolute, we don't really need the absolute value here because for k plus 1, that factor, that's always going to be positive, so I can just bump out that k plus 1. And so I have k plus 1 times the absolute value of x. And as k is approaching infinity, well, what's going to happen? We're going to get infinity over here, right? Infinity times, well, something non-zero, or hopefully non-zero, and because that wouldn't work here. And so we'd get infinity. So let's remember what happens with that, right? When will infinity be less than 1? Well, it won't, right? So therefore, by the ratio test, the series diverges for all x values, right? Because, and again, not 0, because we couldn't have a 0, right? And converges only at its center 0. And so what that means is we see that it's centered just at 0. It's just that one point. And so, right, if we plugged f of 0 into our sort of original scenario, we would get 1. And so in that case, you can kind of take a look at page 649 in your book if you'd like to do that. And so that's one of our scenarios when it's sort of diverges in theory for all numbers, except for when it's at its center, because it's that point, right? And so the radius is 0 and the interval is also 0 because we're in that scenario where it was just at the C. And since we just had this absolute value, right, is greater than 0, we can see that it's centered at 0. Example 4. So we've got, oh, it's kind of a cool one because it looks like we've got sort of an alternating scenario here. And so when we have this, it says find the radius of convergence again. I'm just going to move this here. I tried writing it with the Smart Notebook and it just wasn't that great. But maybe I'll try on the next one because we'll see. All right. So again, we are going to use the ratio test. So you can see, for example, 4, we have x to the k plus 1 over 3k plus 1 over, or times k plus 1 plus 1. So we've plugged in that next term. And over here we have that, remember, it was like a fraction over the original. So we have the keep it, change it, flip it. And that's what this is, right? This is the, like the bottom ratio, like, you know, it's technically in the real denominator, right? So we kept it, changed it, flipped it. Now you might wonder, well, what happened to that -1? Well, it's in an absolute value. So -1 to some k or some k plus 1, and the absolute value, well, that's just going to be 1. All right, so then we can simplify. We can move our k plus 2 over here. They're all factors, so we can all multiply them together, and then we can cancel out. So you can see the x to the k, x to the first, and so that's why the x to the k is canceled, so we're left with this x to the first. And then we have 3 to the k over 3 to k plus 1. And then we can simplify that as well, right? That's a 3 to the k times a 3. So the 3 to the k's cancel, and I'm left with a 1/3. And when we look at this scenario with k's, we see that as k is approaching infinity, well, we have k to the first here and k to the first here. We know that that's going to be the ratio of the coefficients, which is really just going to be 1. So when we have that, we have x times, or what we have next then is the absolute value of x times 1/3, because we've sort of taken that limit now. And since there's no k's here, right, that's our leftover. So this equals the absolute value of x over 3, and that will converge when it's less than 1. So when is that going to be? Well, that's going to be when, multiplying both sides, oh wait, we've got the absolute value of x is less than 3. Okay, so now we have to take a look at what our endpoints would be. And in that case, let me see if I can move these here. We're going to have from 3 to -3, right? And so let's check -3. Well, when I plug -3 into our original series, let's see what happens. So we plug -3 in here, and that's really the only x value, right? Yep. And so then that turns into, well, this is like, maybe I'll get this up just to show you. So this right here, since I have a -3 to the k times a -1 to the k, I can write that as -3 times -1 all to the k. Okay, and so that's just going to be 3 to the k, which is this 3 to the k here. And then 3 to the k times k plus 1 is 3 to the k times k plus 1. Then, I didn't like that's there, but okay. So then that is going to be 3 to the k over 3 to the k can cancel, and then becomes 1 over k plus 1. So how do we then check to see if this is going to converge? Well, we can use a limit comparison. And I know that a similar series would be the series with 1 over k, which I know is the harmonic series, right? And we know that that diverges. So remember, the limit comparison says that if we do the ratio, if we get a positive and a finite limit, then we would have the same sort of behavior. So when we do that, when we take 1 over k plus 1 over 1 over k, and we're finding the limit again as k approaches infinity, that's going to be the same thing, keep it, change it, flip it, as the limit as k approaches infinity of k over k plus 1, which we know will be the ratio, the leading coefficients, the ratio of the leading coefficients, and that equals 1. And so since that is positive and finite, we're going to have the same behavior as the one we compared it to. And since the one we compared it to diverges, this too will diverge. So -3, sorry, you do not get to be included because we saw it diverges there. So let's take a look at 3. When I plug 3 in, you can see that that -1 is going to stay, right? Because I have a 3 to the k over a 3 to the k, and that gives us, well, that gives us an alternating series test, right? And so in that case, I feel like I should have parentheses here. Like this. There we go. Okay, so that's going to be an alternating series. And so how do we do an alternating series test? Well, we have to prove kind of that nth term test, right? We have to prove that the limit as k approaches infinity equals 0. And we can see that it does. Right? Would be bottom heavy. We kind of talked about that already. And so that's going to be 0. And then we have to also prove that it is decreasing. So is the next term less than the previous term? And we can see that, yep, because we would have a bigger denominator, which makes the overall number less. So both those things are true, so it converges. And so we see that it will converge at 3, and we can have that inclusive bracket there at 3. So the interval of, so we can say it will converge in this interval of convergence between -3 and including 3. And the radius is 3. All right, showing that over there. All right, and then we get to our last example, example 5. Again, is this converge or diverge? Find the radius of convergence. So we're going to use, yes, again, the ratio test. And it's probably one of my favorites, and we get to use it a lot in practice here. So again, we get to do the k plus 1 and the k plus 1. Keep it, change it, flip it. Here's the original, so I'm multiplying by the reciprocal. And so you can see with the denominators here, I kind of moved them. Since they're factors, I can just write them in a different order, right? And so then I can see that as the limit as k is approaching infinity, here we will just get a 1 because we have similar powers. So that's going to be the ratio of the leading coefficients. So that part will just be 1. Here, we're going to simplify. X minus 5 to the k times x minus 5 to the first. So the x minus 5 to the k's will cancel, and we're just left with the absolute value of x minus 5. And so this will converge when it's less than 1. And so we can see that, okay, well, that's between 1 and -1, right? That's an absolute value, or the absolute value, right? We can see that this has to be less than 1, which means it has to be between -1 and 1. And so here you can kind of see that, like, hey, what is in the middle here, right? 5 is in the middle. It's our center. Right? That's kind of cool. Okay, so then what's that going to be? We're going to add 5 and add 5, and so we get between 4 and 6. So we have to check the endpoints. So I hope you see that for each problem, it's very similar, the process, right? We're doing the ratio test. We see when, if it will, or will it always be less than 1. And so if there's an x left over, we can then solve for the interval. We can see if the limit is always less than 1, we can say, oh, well, it's always going to converge. If we see that it's greater than 1, then we say, oh, well, it diverges, but except for at that center, we'll just have that 1 point. So anyway, here we are doing this process again, the ratio test. We find the endpoints, we gotta check the endpoints, right? So we'll plug 4 into our original series, and we say, okay, at this point, will this series converge or diverge? So when I plug in 4, well, that gives us a -1 to the k on top over k squared, and hey, that's an alternating series. And we can see that that one's going to converge with our same scenario, right? We have to make sure that the limit as k approaches infinity equals 0, which it will. And we can see that it's going to continuously decrease because if I do a k plus 1 down here, we can see, yep, that will be a smaller number. All right, so 4, you get to be included. And then 6, we can plug 6 in. Well, this is not alternating anymore, so I have to use something else. And I say, oh, wait, this is just an exact p-series. And we see that it's 2, which means you have to pee a lot, right? And so you have to converge to the bathroom. And so that was, I mean, whatever it takes to help you remember, right? But we have the p-series, and we see that since k is squared in the denominator, that this will converge. And so 6 gets to be included as well. So you can see the radius is 1 because we're, you know, that 5 is right in the middle there. And then the interval of convergence is from 4 to 6, inclusive of including the endpoints. All right, so hopefully that was helpful. If you need more examples or just somebody else maybe with a lower pitch voice explaining these examples to you, I have an extra video here for the radius and interval of convergence. Here are corresponding U of T questions. Remember, these are just so that you can get feedback. So just more practice, you can kind of test yourself. I'm not grading U of T any longer this year. It's just there to give you feedback. So I've just kind of opened it up. Even if it kind of gives you a score, I am not putting them in the grade book. It is solely for you to practice, so you have those to work on if you'd like. There's one other power series that's kind of cool that falls in here. These are the next U of T, and it's a power series. This is just kind of leading into next week. It's one of the 4 that I gave you on the sheet in class, and you can see that this is a special one. It's not just the function 1 over 1 minus x, but this is actually really cool. This is a geometric power series. So we've seen this on our sheet before. We just didn't quite get to the day where we were going to make the connection that, hey, this is actually geometric, because, hey, remember that this is really just like 1 times some rate to the n, where the rate is less than 1, the absolute value of the rate is less than 1. And so then we'd be allowed to use the summinator for infinite series, right? And in this case, when it's just sort of this, in a way, parent, right? You can see that the first term was 1, and then it's 1 minus the r. So I just wanted you to see that connection. And I have a video over here that gives you some more information on that supplement. All right, so with that, hopefully it was helpful. I have a joke for you. If you've made it this far, you deserve a smile. What is the derivative of Amazon? And I should do something like a pause button, or you can pause yourself, like pause, think about it. Is this pause? Okay. What is it? The derivative of Amazon is Amazon Prime, of course. It's a good one. Okay. A little bit of cheese for yourself, and there you go. All right. So with that, have a great week. You can take a look at the rest of the Schoology stuff. I'm just going to see if I can pull that up for you here. But maybe not. Okay, never mind. All right, so on Schoology, I have a practice, 6 questions, a practice of 9-8, and the key is included as well. You can leave questions in the Google Form document or drop into one of my office hours on Thursdays from 7 to 8 p.m. or Fridays from 11 a.m. to 12 p.m. Have a great week, and I'll talk to you soon.